Okay, so thank you so much for the invitation to speak at this conference. It's a real pleasure to be here and to see lots of old friends and colleagues as well as new faces in the audience. I'm Pete Shadbolt. I'm a co-founder of PsiQuantum. And today I'm going to try and tell you a little bit about some of the applications work that we've been doing, as well as just a little about the company itself. So in terms of an agenda, first of all, I'll just give an introduction to PsiQuantum for those of you who are not familiar. Then I'll talk about the general problem of trying to solve computational chemistry problems using quantum computers, which is something that we care a lot about. Then I'll talk about a specific example of fault-tolerant resource counting for a battery chemistry problem that we've been working on with one of our automotive customers. And then finally, I'll talk about, where's that quantum computer that we've all been waiting for. So PsiQuantum, we're based in Palo Alto, just down the road here. We're a startup company. We're about 5 years old. And we're really formed with a singular goal of building a large-scale fault-tolerant optical quantum computer, so an error-corrected machine. That's the only thing that we're trying to do at PsiQuantum. And it's an extraordinary team of people, semiconductor engineers, packaging, assembly, photonics, cryogenic systems, error correction, fault tolerance, quantum algorithms, nonlinear quantum optics, pretty much everything under the sun in that building. And it's an extraordinary privilege, for me to be able to work with that team every day and also to present their work. And I hope that I can do it justice today. So as I said, PsiQuantum was founded in 2015. And my co-founders and I think, all signed up to a thesis that goes something like this. First of all, error correction, we believed when we started the company, would probably be required for any commercially valuable application. So we had been working for a combined 60 years or so in academia, and this was really our consensus when we started the company. And of course, it had been known for a very long time that if you want to do quantum error correction, you're going to need a very big quantum computer. So if you read Jeremy O'Brien, if you read Jeremy's PhD thesis, he's now our CEO, but 20 years ago, he was a young PhD student. It says at the very end of his thesis, we're probably going to need error-corrected quantum computers, and error correction is probably going to require on the order of 1 million qubits to do anything useful. And similarly, in my undergraduate education, I distinctly remember being told by my lecturer that the only reason we were sitting in Leeds talking about quantum computing is that the threshold theorem exists and that it's known that you can do error correction. And I think the story is still very much the same today. You need millions of qubits to do anything useful as far as anybody knows. And we also believed when we started the company that if you're going to try to build a really big quantum computer, photonics is a beautiful platform in which to do that. It has very significant advantages for the scaling challenges that you encounter, the engineering challenges that you encounter when you try to build a really big quantum computer. And yeah, maybe 5 years after founding the company, the only thing that I would change here is to remove the word probably. I think I'm more convinced that you need error correction than I've ever been. And so given that goal, lofty goal of a big error-corrected machine, that's really been influential in the philosophy and the kind of approach to engineering and the roadmap that PsiQuantum has chosen. So I think it's fair to say a lot of quantum computing companies got started with the philosophy that you see on the left here. Build a small quantum computer, something that's maybe a little bigger than what you had in a research lab, and then try to make it useful. And as an entrepreneur, as a scientist, as an engineer, I'm extremely sympathetic to that approach. That's a very, very sensible approach. It makes a ton of sense. But for us, given that we knew that the goal was so far from where we had started in the university, we took a very different approach, which is that all of the money, all of the time that we've been very fortunate to have has been exclusively invested into technologies that we think actually have a path to the endpoint. And so, this rocket engine on the right-hand side, in this instantiation, it doesn't even go a foot off of the ground. But I would much rather have a rocket engine than a stepladder if I recognize that I ultimately have to go to the moon. So apologies for the philosophizing. I'll stop philosophizing now. And I also want to emphasize that we did our time on the left building small quantum computers. So this is the chip that I was extremely lucky to get hold of a decade ago now, back in 2012. And this is a 2-qubit quantum processor with a photonic chip. Photons come in the left, they go out the right into single photon detectors. And this was a very small 2-qubit processor, CNOT gate, some single qubit rotations, somewhat programmable, and a really awesome platform to play around with entangled photonic qubits on a chip. In fact, this was one of, if not the first, quantum processors of any kind on the internet. We hooked it up to the web with a HTTP API and stuff like that. And it was really fun exercise, and also kind of characteristic of the type of work that we were doing in the university at the time. Here's a much bigger circuit. I think this is a 6-mode arbitrary unitary operation. So again, a big glass chip here. Photons come in and out the bottom of this chip. And you can reconfigure this and run algorithms and do synthesis of high-fidelity gates and publish a lot of science and nature papers, basically. That's what we were doing in those days. Similarly, even more complex circuits, 16 single photon sources, fairly interesting, complicated, entangled states. And you can see lots of gold, lots of metal in this photograph to control many, many phase shifters inside that interferometer. Probably the result that's gotten the most airtime at Q2B over the last few years is the variational quantum Eigensolver. This result, I was extremely lucky to be involved in this. The team from Harvard, so Jared and Manhong and Alan and so on, had come up with this algorithm and brought it to us right when we had a very flexible piece of hardware that just happened to be right to implement that. And so we got to do the first demonstration of quantum chemistry on a chip using this new algorithm that seemed really exciting at the time. And so you send some photons into the chip, you entangle them, you persuade them to behave a little bit like the electronic structure of a molecule, and you can extract energies of that molecule. In this case, helium hydride, the strongest acid in the universe, and a conveniently very small molecule for our very small quantum computer. And in the end, you get graphs like the one that you see, which is showing that the helium atom and the hydrogen atom like to hang out 80, 90 picometers away from each other or something. And as a young PhD student, this was really exciting, right? We'd been playing around with this photonic hardware, and suddenly it was actually producing numbers that were chemically meaningful. Of course, it's a pitifully small quantum computer and is going to lose even against a pocket calculator, but it was really cool to see that kind of end-to-end chemistry algorithm running and really inspirational for me. And I think that VQE and similar experiments that have been done by many fantastic groups around the world since answer this question here, which is, do quantum chemistry algorithms work as expected in toy quantum computing hardware systems? Emphasis on toy. And of course, this question has been answered in the affirmative very, very strongly. Yes, you write the code, you implement the gates, and you get the numbers that you would expect to see. But we're at Q2B, and we're very grateful to have lots of big corporations here who want to use quantum computers for their business. And I think that if I were in such a position, I would want to answer a different question, which is, as far as I'm concerned, will quantum chemistry algorithms running on a quantum computer ever deliver commercially valuable applications? And moreover, when will they do that? How will they do that? By what means? And how confident can we be today that that's actually going to transpire? I think that's a very different question, and I think that's a more exciting question to answer. And to answer that, we got to do something different to 2-qubit photonic chips. To answer that question, we got to do some math. And so here's a sketch of the variational quantum Eigensolver, and I'm picking this over QPE just because it's kind of easier to talk about in this instance. But it's a very simple story. We do quantum state preparation on the left. So we run some quantum circuit that prepares our qubits in a state that somehow represents a delicate, a complex arrangement of electrons in a molecule. And then in VQE, what we do is just measure that state of qubits. We get some energies. And then we can calculate the energy of that electronic configuration. As you know, molecules like to hang out in low energy configurations. And so we can simulate that relaxation just with a conventional optimization algorithm running on a regular CPU. We run that feedback loop, and eventually we find the ground state of the molecule. And when we wrote VQE, when even prior to that and since, everybody knew that the devil was in that quantum state preparation box. Because if you look inside that box, you find all sorts of nasty stuff, like Jordan-Wigner, like trotterization, all of the business of preparing, again, this pretty complicated and delicate quantum state that represents the configuration of your electrons. That's not something that you get to do for free. And in fact, for realistic instances, that's going to take billions of gates to implement. So this, by the way, shouldn't be terribly surprising. If you think about your laptop has a gigahertz clock, does about 1 billion things a second, and it takes about a second to do anything computationally interesting. And so that's 1 billion operations. And with very wide error bars, quantum computers seem to be in about the same ballpark, billions of gates to do anything useful as far as anybody knows. That, of course, is a big problem, given that if you pick up any quantum computer today, including ours, you're going to see a graph like the one that you see on the left here. Most quantum computers have physical error rates on the order of a fraction of a percent. And so by the time you've done 10 to 100 things, the machine is pretty well swamped by noise. And that's a big problem when you need billions of gates. And so when we started the company, that's why we chose to exclusively try to build machines that operate more like the figure that you see on the right. They're continuously suppressing error, and in doing so, hopefully get out to this regime of very, very low error rates and very deep gate depth. In fact, regardless of the path that you pick, whether you go down a NISQ trajectory or whether you're building fault-tolerant quantum computers, I think this exact statement actually still holds for both sides of the coin, which is that the gate depth of current quantum algorithms is too large to be practical. In the NISQ case, that's because you get swamped by noise before you get useful answers. And in the fault-tolerant case, it's actually because by the time we compile these quantum algorithms and account for all of the overheads of Jordan-Wigner and trotterization or qubitization or whatever, you end up with something that's so deep that even with a really fast, really good quantum computer, it might take a year to get an answer to your computation, at least in a naive implementation. And so this statement holds for everybody right now. But let's try and do something about it. And what we can do about it is better compilation. And this is really the one point that I want to emphasize in this talk. If there's only one thing that you take away, I would hope that it is this, which is that there's lots of smart people around the world trying to solve that problem, trying to find free lunches and remove complexity from these algorithms in just the same way as we design better code and improve our conventional algorithms. But whether you pick NISQ or fault tolerance makes a huge difference as to the nature of that technical work. What I mean by that is that in a NISQ machine, and there's lots of people in this room who do this type of work. I've done it myself in that VQE experiment. What you're typically trying to do is to take some algorithm that maybe does quantum chemistry and squeeze it into a piece of hardware with a handful of qubits and a handful of gates. And in doing so, what you encounter is that typically the single qubit gate operations are pretty nice. And it is the 2-qubit gate operations, like controlled NOT gates, for instance, that tend to be the slower, noisier, more expensive gates. And so you get into this kind of compilation activity of desperately trying to remove controlled NOT gates from the circuit and not worrying too much about single qubit gates. And what is kind of pernicious and maybe a little counterintuitive is that that situation is completely inverted once you pick a fault-tolerant target. So in an error-corrected quantum computer, surprisingly, it's actually the single qubit gates, specifically the T gates, that are extremely expensive. And 2-qubit gates are, relatively speaking, almost free. And so there are two teams of people who are doing almost diametrically opposed scientific work. And I've spoken to a lot of people in the community who are maybe a little concerned about some of this. So I think this statement, I think, is fair, which is that if you believe, like us, that fault tolerance will be required for commercial applications, and that's, of course, a belief. The jury is out. It's absolutely possible that we will find commercially valuable NISQ applications, but we believe that fault tolerance will be required. If that's the case, you should work on removing T gates and not C0 gates. So again, we're at Q2B. There's lots of businesses in the building here, and you would be forgiven for saying, hey, Pete, that's all nice, but you're talking about T gates and magic state distillation and error correcting codes. Surely these companies don't care about that stuff, right? Maybe they're just getting started programming a 2-qubit processor or something like that. And actually, one of the most gratifying things for me as a former scientist and now entrepreneur over the last 5 years has been to see the incredible level of sophistication that has been built inside some of these organizations. So these guys have been hiring PhDs in quantum information. They've been reading papers. They've been doing work, writing code, and getting really serious, and now are coming to us saying, we want to do fault-tolerant resource counting. We want to figure out what is required to run code on error-corrected quantum computers. And so, we're really lucky to have a bunch of customers across customers and partners across all of these verticals, mostly from Fortune 500 companies. If I sent that message back in time to my former self, I think it would have blown my mind that people from car companies are doing fault-tolerant resource counting. It's awesome. And so that brings me on to this specific example of lithium-ion battery chemistry. Of course, we want to build better batteries for our cars with longer range, better capacity. We don't want them to catch fire on the freeway. And I won't pretend to be an expert by any means, but I do have a tiny bit of experience. I spent a summer many, many years ago with my arms in a glove box like this, mixing up chemicals at random, trying to build better lithium-ion batteries, polymer lithium-ion batteries at the time. And these gloves are really sweaty in the summer. If it's a hot summer and you spend all day with your arm in the glove box, you start to think, hey, maybe we could do this with a computer. That'd be nice. And so that's the dream here, is to do that all in the computer, simulate it. Just very briefly on lithium-ion batteries, okay, we have an anode, we have a cathode, and we have an electrolyte consisting of a solvent and some salts floating around in the electrolyte. When we charge that battery, the electrons head up through the wire, and the lithium ion becomes positively charged and is transported together with some of those salts in the electrolyte over to the cathode, where it reunites with the electron. And if we zoom in on that interface between the electrolyte and the cathode, the first time that you charge a lithium-ion battery, something very interesting happens. A layer of what is best referred to as goop or crud or something like that forms on the surface of the graphite cathode. And although these are small molecules, the chemistry of this is really poorly understood. Despite big efforts of computational chemistry, all sorts of experimental work, what is going on at this interface is poorly understood by chemists. And so this is the specific computational chemistry problem that our customer came to us with. And starting from that kind of poorly understood behavior, we then went into what is now a multi-year effort of end-to-end fault-tolerant resource counting. So we start with that use case, and then we go all the way through the algorithm, the error-correcting code, and down to the photonic hardware, together with a global optimization of that fairly complex recipe, with the hope of being able to make concrete statements as to what we're going to do with machines of what size, with which precision, and so on and so on. So these are the statements that we're really trying to extract at the end. Given an error-corrected optical quantum computer with some footprint, with some error rate, which properties can we calculate, with what precision, and how long is it going to take us to do that. Just as an aside, this process of going all the way from the very top of the problem to the very bottom has a close analogy with what we do inside the company in building optical quantum computers. So the architecture, the recipe for an optical quantum computer is pretty complicated. And in order to have confidence that it's going to work, we have to do very detailed and very thorough error modeling. And we're really proud of the fact that we've been able to build what is a 25-person team now that's been working for the last 5 years to take 25 different sources of error: waveguide loss, detector inefficiency, dark counts, source impurity, dispersion, you name it, turn them all on at the same time. So you don't just pick one, you assume that all of these bad things happen, and then run them through a multi-scale numerical model that goes all the way from the basic hardware, the photonic components, which in some cases, those error models are informed by hundreds of wafers worth of silicon, hundreds of thousands of measured devices, through the circuits that we use for multiplexing, the resource state generation, the error correcting code, and ultimately all the way up to encoded gate operations, such that we can now do cool stuff like that T-gate that I showed previously. It's just a rectangle on the PowerPoint slide. In reality, it's an incredibly complicated system of entangled photons. And we can look at the behavior of that system in terms of very fundamental low-level error rates like dispersion in a waveguide or detector dark counts. And that ability to do this with confidence is an extraordinary accomplishment of our architecture team at PsiQuantum, and is analogous to what we do here in resource counting for chemistry. So we take these various molecules. These are molecules that are floating around in that electrolyte and that ultimately contribute to the layer of crud that seems to be so important and that stops our lithium-ion batteries from catching fire. And we basically are trying to solve the Schrodinger equation and figure out the electronic structure. That's the information that we ultimately want to be able to give to chemists. In doing so, we make a whole list of subjective choices as to the design of this algorithm. Some of these are informed by the community, some of them are informed by us. But to cut a very long story short, we don't use variational quantum eigensolvers. VQE is kind of nice for small-scale experiments, but we're actually gone back to the old school with quantum phase estimation in this instance. We don't use trotterization. We use something called qubitization instead. Rather than running T-gates in serial, we're actually able to run T-gates in parallel, which is something that we kind of did quite a lot of work on in this result. And then we also deploy a trick from photonics that I'll talk about in a second to make the whole thing considerably more efficient. Anyway, we pick an algorithm, we write some code, we compile that into a gate sequence. Here you can see a whole bunch of things that you can fairly think of as subroutines running in that algorithm. And once we've specified that at the circuit level, then we need to look under the hood and think about accounting for fault tolerance and error correction. One of the really interesting things for me as a casual observer of this work has been to see that the amount of resources required for magic state distillation is actually much smaller than you might have anticipated. Certainly when we started the company, a lot of people were afraid that the magic state distillation that's required for T-gates and these expensive single qubit operations would absolutely dominate the machine. And here we see that that's actually not the case. So that's a really encouraging result that's kind of the product of a multitude of compounding effects. And then beneath that layer of error correction, we also look at the specifics of the photonics implementation. There's a lot to say here, and I don't really have time, but I will point out one specific trick that we play, which is to exploit the fact that in a photonic quantum computer, and indeed in many other platforms, you are inevitably going to put qubits into optical fiber. And once you have qubits in optical fiber, you suddenly have a tremendous amount of flexibility, especially in the time domain. And you can make very interesting trade-offs between space and time. Of course, space-time trade-offs are very old. They exist for conventional computers. People have talked about space-time trade-offs for optical quantum computing for many, many years. What's interesting about this specific trick, which is called interleaving, is that we figured out how to do that in a way that navigates around the constraints of error correction and fault tolerance. If you do that naively, you are not going to be able to do that. But this is a paper that's now on the archive. You can take a look at the details, and turns out to be really profoundly important for actually making these applications practical. And so I won't go into the details here, 100 orbitals or so. And here you can see numbers for the size of machine that we need and the runtime that we need. And the short story is that when we started this project, it was looking like weeks to months of runtime to calculate relevant properties of these molecules. And by the end of the project, we were in the regime of being able to do that in about a day. So on our future machine that we expect to have, these algorithms look like they would take about a day to run. And so to sort of summarize that, we're now in the position where we've actually gone from end to end. And we can make statements that, to me, seem really kind of concrete and valuable. We have an algorithm, and we have code to implement full configuration interaction simulation of molecules that clearly pertain to lithium-ion battery chemistry on a fault-tolerant optical quantum computer. We've properly accounted for the resources required, and those resource requirements are pretty close to what we believe will ultimately be practical. There's probably still some more work to do, but there's very good reasons to be optimistic. Here you can see some of the public data on resources required for a whole diversity of algorithms, and you can see that these numbers are coming down very rapidly. So on the y-axis here, this is the volume of quantum computer that you need. The x-axis is time, and I think these curves are very encouraging. We expect to continue on these types of trajectories. And so this is very much a go as opposed to a no-go for lithium-ion battery chemistry on a quantum computer. So in the last couple of minutes that I have available, just touch on this question, which is, where's that quantum computer that you guys have been talking about? And again, when we started the company, it was with the understanding that basically anybody can build a qubit today, whether it's quantum dots, NV centers in diamond, superconducting qubits, photons, everyone can build qubits. And we're seeing beautiful results at this conference and elsewhere that show that problem is under control, if not completely solved. And really, we thought when we started the company that the problems to solve was something else. They were scaling problems and engineering problems. And from my perspective, they are manufacturability, cooling power, connectivity, and control electronics. I think that these are the things that are really stopping all of us from building big enough, useful quantum computers. So you need to be able to manufacture, yield, integrate millions to billions of devices. You need way more cooling power than anybody's got today. You're not going to fit 1 million qubits onto a single chip, so you need an interconnect to connect things together. And somehow you need to control and look after what is an extremely complex machine. And so you need to bring CMOS electronics close to the qubits. And so we've set out to solve these problems, and we think that photonics has very, very big advantages in solving these challenges. Here is the product of a huge amount of work over the last couple of years. This is a 300 millimeter silicon wafer built in a tier 1 semiconductor manufacturing context, shoulder to shoulder with laptops and cell phones, essentially. It's a 25-layer, 500-step manufacturing process. We've been through about 1,000 wafers worth of silicon so far. And on board this wafer are tens of thousands of quantum devices, including superconducting single photon detectors and single photon sources. So on the one hand, this is a boring standard semiconductor manufacturing process. That's what we want in order to have a hope of delivering a very large number of devices. On the other hand, there's some extraordinarily exotic physics going on inside this wafer. The laser that we shine into that chip is about 1 trillion times more intense than the single photons that we detect. And we even have crazy stuff like thermal heaters that are close to room temperature on the same chip as superconducting detectors at 2 Kelvin. And we've made it work, which is pretty extraordinary accomplishment of the team. This is what it looks like inside the factory. This is what it looks like from above. And I do want to emphasize, we're not going to these big factories in order to mass manufacture quantum computers. We're going to these big factories because the semiconductor industry has collectively invested about $1 trillion over the last 50 years, figuring out how to put 1 billion transistors into your pocket. And we want to access the incredibly advanced tools, the incredibly high performance manufacturing that we believe is actually required to build devices that meet the requirements for fault-tolerant implementation. Here's the tester testing those devices. This is what our cryostats ultimately are going to need to look like. So today we have a small lab in Palo Alto, but ultimately we're going to need something like this. This is a system built by our Chief Product Officer, Nicholas Clares at the Stanford Linear Accelerator. To put it in context, our current cryostats have about 1,000 times more cooling power than you get at millikelvin temperatures. That's simply by virtue of the fact that we run close to 4 Kelvin. But this thing has 1,000 times more cooling power again, and that's ultimately where we got to get to. This could be a picture of any BGA chip, but this is our BGA chip. This is a control chip that we've been working on for some time. It's now under cryogenic test. It's got about 750 million transistors on it. It's built in a 22 FDX CMOS process, and it lets us drive and read out photonic qubits. We're really excited to share some results on this pretty soon. And then finally, this is the team of people who did all of the work. I just raised the money, and I'm so happy to be able to present their work. I really hope I've done it justice. Sam Pallister in the hot dog costume on the right there leads our applications team and did that lithium-ion battery chemistry work together with his team. And yeah, if you want to come and figure out whether quantum computers are ever going to help your business or work with us on some of the hardest engineering problems on the planet, please get in touch. It would be a delight. And thank you so much for having me.